All right, welcome everyone. Today we're going to consider one other type of improper integral, and that's where we have a discontinuous function. So the function we're trying to integrate has a discontinuity somewhere on the interval that we're trying to integrate over. So this could happen in a few places. It could happen at one of our endpoints, so it might happen at x equals a or x equals b, or it might just happen somewhere in the middle, so some number c in the middle, in between a and b. So what are some of the types of discontinuities we might encounter? We might encounter jump discontinuities or removable discontinuities, and those for the most part are okay. We can integrate those. The ones we're going to be looking at today are where things might get a little difficult, and that's with infinite discontinuities, where we have our graph has a vertical asymptote. So how are we going to handle these? Well, let's start with the definitions. So we're going to kind of break this apart just like we did with the other improper integrals we saw, where we had infinite limits or infinite intervals. But now we're going to be having discontinuities. So let's consider the left-hand case where we have this function f. It's continuous on the interval from a to b, but it has a discontinuity at x equals b. So that's why we're using this open interval notation at x equals b. So it has a discontinuity there. So that means this is not a usual definite integral that we really know how to calculate. We have to adjust this definition a little bit because our function is discontinuous at that upper limit. So our function is discontinuous at the upper limit. How are we going to do this? Well, we're going to use limits. And we're going to write this as the limit as we approach that discontinuity. So we're going to have just a regular definite integral here, the integral from a to t of f of x dx. And we're going to see what happens as that upper limit gets closer and closer to that discontinuity. We're going to approach that discontinuity and see what happens. And so the way to approach b in this case is from the left. So that's why we're using this left-hand limit notation. Well, we could also have a discontinuity at the other endpoint. So we call these maybe right-hand improper integrals. So we have a continuous function f that's continuous on the interval from a to b, but we have a discontinuity at a. So we're using that open interval notation to indicate that at x equals a, our function is not continuous. It's discontinuous. So that means when we look at this integral notation here, this is not a regular definite integral that we saw back in Calc 1. We have to adjust it. We have to adjust for the discontinuity that's happening at our lower limit there. And how do we do this? Well, we approach that discontinuity. And how do we approach? With limits. So we're going to rewrite this as the limit as our t value, which is going to be our new lower bound, approaches a from the right. So we're going to do the limit of t as t approaches a from the right of the integral from t to b. And essentially what we've done is we've taken that discontinuity off of the integral and we've put it onto this limit. And we're going to see what happens as we approach that discontinuity. So graphically, what these types of things might look like, especially for infinite discontinuities, is we have a vertical asymptote. And what we're trying to do here by calculating these improper integrals is find the area under the graph. But the issue that we're running into is this region extends infinitely far up, or it might extend infinitely far down. But for non-negative functions, usual disclaimer there, for non-negative functions, we can think of these as the area under the curve. And so you can see in this left improper integral graph here, we are running into an issue at our upper limit. So we're integrating from, say, we want to integrate from, say, A to B, but we see that we have this vertical asymptote at x equals b, so our function is discontinuous there. And in some cases, we can still figure out the area under this curve. It's finite. But in other cases, it's going to be infinite. Same thing for right improper integrals. Here we might be integrating from A to B, but now we have a discontinuity, and really the cases we're going to look at are where we have a vertical asymptote or an infinite discontinuity at x equals a. And we might be interested, what is the area of this shaded region? Well, this region extends infinitely far up, so it's unbounded. So, you know, it might have a finite area, but it might not. And that's what really these improper integrals are going to help us do, is figure out if these regions have finite area or infinite area. So this is the kind of the pictures to have in our minds when we're calculating these improper integrals. Now there's one other case. So these were where these two cases, the left and the right here, were where we had a discontinuity at one of the endpoints of our interval. Now we might have a discontinuity somewhere in the middle. So we might have this discontinuity at x equals c, where c is somewhere in the middle of our interval, so it's in between a and b. And how we do this is, if we're trying to integrate our function f of x from a to b, this is not a regular definite integral. Even though it kind of looks like it, it's an improper integral because we have that discontinuity somewhere in the middle. So what do? Well, we split it up into two separate integrals. Each of these is improper. And we split it up at that discontinuity x equals c. So we do the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And we had to split it up right at that discontinuity. So that's an important point here. We have to split it at that discontinuity. And so this is going to be our left improper integral. This is going to be our right improper integral. And in order for this definition to make sense, both of these, the left and the right improper integrals, have to be convergent. So we also use that similar wording, convergent. So one of these types of improper integrals is said to be convergent if the limit exists. And then we also say divergent if the limit does not exist. So we use that same kind of wording here. And so in order for this improper integral to be defined, both the left and the right improper integrals have to be defined and convergent. So we need those to be convergent. And graphically, what does this look like? Well, if we're integrating from, say, a to b, and we have this vertical asymptote, we have this discontinuity at c somewhere in the middle, well, you can see the left improper integral is giving us the area on the left side, and the right improper integral from c to b would give us the area on the right side of this discontinuity. And so that we have this region that extends infinitely far up, and the question is, does that have a finite area or does it have an infinite area? And that's what these improper integrals help us calculate. All right, so let's see an example. We're going to look at a few examples, but before we do that, we want to consider just a few important infinite limits. So for the most part, when we talk about these types of improper integrals, we're going to be looking at where our function has a vertical asymptote. And so the most common one we're going to consider are the c over 0 forms. So this occurs where we have division in our function and our denominator is equal to 0. But the numerator does not equal 0. So that's an important kind of distinction there. So we get these c over 0 forms when the numerator does not equal 0, but the denominator does equal 0. And so let's see how to actually, let's look at a few examples here, and we're going to base these off of what we're going to do in examples 5 and 6. So let's look at the function. Let's flip over real quick to example 5. We're going to be integrating this function 1 over square root x minus 1. And there's going to be something that happens at x equals 1. So let's consider the limit of 1 over square root x minus 1 as x approaches 1 from the right. We just want to see what's happening to this function as we get closer to 1 from the right. Now when we look at this, let's actually just plug in x equals 1. And just see what happens. So when we plug x equals 1 into this, we get 1 over square root 1 minus 1, which is 1 over 0, which that means we have a c over 0 form. All right, so what that tells us, it tells us our limit is one of two things. It's either plus infinity or it's minus infinity. So these c over 0 forms always tell us that we have an infinite limit. We just have to decide, is it positive or is it negative? And the way we decide positive or negative is with a test number. So the first step here for calculating these infinite limits is first to just identify that you have a c over 0 form. And then second, you have to use a test number to decide, is it positive or negative? So x is, in this case, x is approaching 1 from the right. So we're getting closer to 1 with slightly bigger numbers. So we might use a test number like t equals 1.1. It's close to 1, but just slightly bigger. We've added a little bit extra there. And then we just plug it into the function. So we get 1 over square root 1.1 minus 1, which is 1 over square root 0.1, and that's a positive number. Positive divided by a positive. And so that's telling us our limit here is, it's an infinite limit, but it's equal to positive infinity. So we just throw out that other option. So this is how we calculate these c over 0 forms to see if we have an infinite limit, and specifically to see whether it's plus infinity or minus infinity. Now you can play the same game with a lot of our trig functions as well. So it's kind of not as explicitly written, but you can look at, say, tangent. And tangent has a bunch of vertical asymptotes. It actually has a whole bunch repeated. And you could look at, say, what happens to tangent of x as x approaches pi over 2 from, say, the left or the right. It has a vertical asymptote at pi over 2, and it has an infinite limit on both sides of pi over 2. Now, as you look at this, it doesn't look like we have division, but we know we can always rewrite this in terms of sine and cosine. So we could rewrite this as sine x over cosine x as we approach from the left. And you could run through the same process. Plug in pi over 2 to show that this is a c over 0 form, and then use test numbers to figure out if it's positive infinity or minus infinity. So you would go through the same process. So these infinite limits, most of the ones that we see, are going to be of this form. So the special cases, tangent x, secant x, cotangent x, cosecant x. All of those trig functions have vertical asymptotes, so they have these infinite limits. And you can kind of do this type of work to show it. One other case that we're going to be considering is natural log x. So you might see this one as well. And this is where when x approaches 0 from the right, our log function gets really large negative. So we have this other limit as well. So tangent, secant, cotangent, cosecant, those all have infinite limits at various multiples of pi or pi over 2. Kind of have to figure out which based on where sine or cosine is equal to 0. So we won't go through all those cases. But this other one, the limit of natural log x, this happens when the value inside the log function gets close to 0 from the right. And that's equal to minus infinity. All right, so let's actually try an example. Let's look at example 5. So this is going to be calculating. We're going to see how to calculate this improper integral. We're going to determine if it's convergent or divergent. And if it's convergent, we're going to find its value. And we already know, we looked at it, that at x equals 1, this function is discontinuous. And it has an infinite discontinuity. So we know something's happening here. This is not just a regular definite integral, and you can quickly see that. Look at the two endpoints, and we see that we have division. We would have division by 0 at x equals 1. So as soon as you start seeing a division by 0, you know something funny is going on, and you're probably dealing with an improper integral, and that's exactly what we have here. So we notice that something's happening at this lower bound. So our first step in calculating this improper integral is to rewrite it as a limit. So we're going to take that number that is giving us an issue, which in this case is our lower bound, and we're just going to write it instead as a variable, and we're going to let that variable approach 1. So in the definition we use t. I normally like to use a just because t's sometimes start looking like plus signs, but if you want to use t, you can. So we're going to really take this endpoint that is giving us the difficulty, and we're going to rewrite this as a limit where we approach that number. So we're going to let a approach 1. Now, there's two ways we can approach a number. We can either approach from the right or we can approach from the left. And we're going to approach 1 from the right with slightly bigger numbers. Why are we using slightly bigger numbers? Well, because we're looking at the interval from 1 to 4. And so all of the numbers in this interval are slightly bigger than 1. So we're approaching 1 from the right. So this is our first step, key step. Rewrite this thing as a limit. We're rewriting it as the limit as a approaches 1 from the right of the integral from a to 4. We could have used t's here. That's fine as well, just so long you're consistent. And you don't use x. So we're already using x. You just have to use some different variable here. All right, so we've rewritten it as an improper, or as a limit. And now we go through, just like we did before with our other types of improper integrals, and we just go through and calculate this integration. So this is just a regular definite integral. So we can just do this just like we normally would. So let's do it. We're going to have the limit as a approaches 1 from the right. And now we want to calculate this antiderivative of this function. So to help with that, let's rewrite that as x minus 1 raised to the negative 1/2 power. So the 1/2 converts the square root into a power function, and then the negative deals with the fraction. This is just a much easier form to identify what the antiderivative is going to be. And that's what we do next. So let's get the antiderivative. So the antiderivative of this is x minus 1. We keep what's inside of the parentheses. We add 1 to the exponent, so that takes us up to 1/2. We take that new exponent, flip it, put it in front. So we get a 2 in front here. Now, really what we're doing here is a u substitution with u equal to x minus 1. But this is one of our kind of our k-form integrals, our common k-form integrals that it's a mental u substitution that we're doing. So for these, we should be able to just do these without showing all of that work in the middle there. And we're going to evaluate not from x equals 1, from x equals a to x equals 4. All right, so we found our antiderivative. We're going to evaluate it. We still have this limit, so we're still writing this limit as a approaches 1 from the right. We're going to deal with that at the very end. So now we have our antiderivative. We plug in. So the top number goes in first. So we're going to have 4 minus 1 raised to the 1/2 power minus lower bound goes in next. So a minus 1 raised to the 1/2 power. Clean this up. Not too much to do. Maybe we do a little bit of work right here. Just simplifying that down. So we have 2 times 3. And instead of 3 raised to the 1/2, let's just write that as square root 3. And then we have minus 2 times a minus 1 raised to the 1/2 power. We'll just leave that alone. All right, so this is what we want to calculate the limit of. So all of this work was really just evaluating our definite integral, just like we normally would. Find the antiderivative, plug in like you normally would, simplify just like you would. So now the next step, the last step here, is calculate this limit. And whenever we do that, whenever the limit is of a number, is of something approaching a number, first thing we should try is, well, plug in the number and see what happens. If you get a numerical value out, most likely that's what your limit is going to be. And so we can plug in a equals 1 into this function. We get 2 square root 3. There's no a value here, so this doesn't change at all. Then we have minus 2. That minus 2 is also a constant multiple, so that's not going to change at all. And then we plug 1 in, and we get 1 minus 1 raised to the 1/2 power. And that makes sense. That actually does make sense right there. And 1 minus 1 is 0. So this whole second piece here just becomes 0. So the way we evaluate this limit is we plug in, it's a direct substitution, we plug in a equals 1. And we get something meaningful out. So there we go. We have the value for this improper integral. Took a little bit of work to get there. But what this shows is we actually get a numerical value. And that tells us this integral, this improper integral, is convergent. And we know what its value is. 2 times square root 3. All right. Not too bad. Let's try another one of these, just for the practice. So let's look at in example 6, we're going to look at the integral from 0 to 7 of 1 over x minus 5. Now, at this point, any integral that we see, we need to check if it's undefined, if it's discontinuous anywhere. So if we see a fraction, your eyes should immediately go for that denominator. So I see a fraction here, immediately I'm drawn to that denominator, and I'm figuring out where it's equal to 0. And so what we see here is this function is undefined at x equals 5. That's where I would have division by 0. And x equals 5 is inside that interval from 0 to 7. So that means we're trying to integrate this function which has a discontinuity inside this interval. So this is an improper integral, even though it doesn't look like it. So these ones are difficult to find or identify because on the surface this looks perfectly fine. All the limits are numbers. So it looks like we should just be able to find the antiderivative, plug the numbers in, and that's the end of it. But it's not the case. And that's because, kind of sneakily, there's a discontinuity somewhere in the middle of this interval. So this is one thing from now on we're going to have to check. Each time we have a definite integral, you want to really look for where that function is undefined. And for a definite integral, you want to make sure that undefined or discontinuity happens. You want to see if it happens inside the interval that you're integrating over. So it'd be good practice for you. Try to show that this actually has an infinite limit at x equals 5. So it has an infinite discontinuity at x equals 5. Not only is it undefined, but it also has an infinite limit. So that would be good practice. So you'd show that it's a c over 0 form and go through the work that we did for the last example, the function in the last example. All right, so we know that this is an improper integral. And it happens in the middle. So what we're going to do is we need to split this up at the discontinuity. So we're going to split this up into two separate improper integrals. It'll be the integral. So the one we're doing is we're trying to figure out the integral from 0 to 7 of 1 over x minus 5. We're going to write this as the integral from 0 to 5 of 1 over x minus 5 dx plus the integral from 5 to 7 of 1 over x minus 5 dx. And we're going to calculate each of these separately. And notice that because we have this discontinuity at x equals 5, we had to split up this integration at x equals 5. And so what we're going to do is we're going to go through and calculate each of these. And in order for this to be convergent, both of these need to be convergent. And that's going to be a key thing to remember here, is both of these need to be convergent. So if we're going along in our work and we find that just one of them is divergent, then we can stop. Automatically, the original improper integral is divergent. So both of these need to be convergent for our original one to be convergent as well. So let's start with this integral from 0 to 5 of 1 over x minus 5. We could start with either one, but let's start with this one. So we're going to do the integral from 0 to 5 of 1 over x minus 5 dx. So we know this is an improper integral, and we know that it's where the discontinuity happens is at our upper limit, at x equals 5. So the first step in calculating this limit then is, or this improper integral, is to write it as a limit. So we're going to see what happens to our function 1 over x minus 5. And we're going to integrate from 0. Now that discontinuity is happening at 5, so we can't just plug in 5, we have to approach it. So we're going to approach x equals 5. So I'm going to use a variable up here. I'm going to use b. We could use t. And what's going to happen is we're going to approach 5. So we're going to let that new upper limit, that variable b, we're going to let it approach 5. Now, which direction are we approaching 5 from? So we could approach from the right or from the left. So if we consider our interval here, we're looking at the interval from 0 to 5. And so all of the numbers in this interval are slightly smaller than 5. So we're going to approach 5 from the left. Take a little bit away. We're slightly smaller than 5. So we use that 5 minus notation. All right, so this is the first step. Rewrite it as a limit. So our function has a discontinuity at x equals 5. So we have to rewrite it as a limit. We have to take that x equals 5 value off of our definite integral, and we have to approach it. So we're writing it as the limit as b approaches 5 from the left of the integral from 0 to b of our function. All right, so that's the first step. Key step. We have to rewrite it as a limit. Now we just go through the integration. So this, just like before, is just a nice regular definite integral. There's no discontinuities here to worry about because we've taken that discontinuity off and we're approaching it. But in between 0 and b, everything is perfectly fine. So this is just a regular definite integral we can do. So let's do it. We're going to save this limit till the end, but we still write it. What's the antiderivative of 1 over x minus 5? Well, it's the natural log of absolute value x minus 5. Again, there's kind of a substitution rule here. So if you wanted to, you could go through. We're letting u equals x minus 5. But this is one of our usual k-form integrals. So, you can just do this one without showing all the work. We're going to evaluate that antiderivative from 0 to b. Plug in. So top number goes in first. So we get natural log of b minus 5. Bottom number goes in second, so we plug 0 in. So we get natural log absolute value 0 minus 5. And it's important that you remember the absolute values here because otherwise this part wouldn't make any sense. Neither would this. So, sometimes you can get away forgetting with the absolute value when you integrate to get these natural log functions. But this one we actually do need to remember the absolute value. So that's a good habit to get into. Remember the absolute value when you integrate to get a natural log function. All right, so we've evaluated. Let's simplify this just a little bit. Not too much to do in that first one, but here we can simplify. So 0 minus 5 is negative 5, and the absolute value of that is positive 5. So we end up with just minus the natural log of 5. That does make sense. All right, so we want to figure out this limit. So all of this work so far was just calculating that definite integral. So finding the antiderivative, evaluating the antiderivative, simplifying, and now we've gotten it to a point where we're ready to actually compute this limit. And so we're computing this limit as b approaches 5 from the left. So let's think about it. As b approaches 5 from the left, what's happening to the absolute value of b minus 5? That's what's inside our log function. So let's consider what happens to that term absolute value b minus 5. So if it didn't have the absolute value sign there, as b gets closer and closer to 5 from the left, this would approach 0 from the left. So it'd be, these values would be slightly smaller than 5. So then slightly smaller values minus 5 would give you a negative number that's getting closer and closer to 0. But the absolute value is going to make all of those negatives positive. So this whole expression here, absolute value b minus 5, as b gets closer to 5, this is going to go to 0. It's going to get closer and closer to 0, but it's going to do so from the positive direction with slightly positive numbers, slightly bigger than 0. So as b gets closer to 5 from the left, this absolute value b minus 5 is getting closer to 0, and it's getting closer to 0 with slightly positive numbers, just slightly bigger than 0. All right, so what happens to our log function as the term inside the log function gets closer to 0 from the right? Well, we know that it's equal to minus infinity. And this is one of our special cases. The limit of natural log x as x approaches 0 from the right is equal to minus infinity. So this natural log term, as the term inside of it gets closer to 0 from the right, the whole log function gets larger and larger negative. And it doesn't matter that we're subtracting this minus this natural log 5. This term here is getting larger and larger negative, so subtracting off natural log 5 is just going to make it, a larger negative number. So as b gets closer to 5 from the left, this limit is minus infinity. And so what that means is it means this improper integral is divergent. And if we go back, what we've just shown is that this improper integral is divergent. So if we go back, it means our original improper integral is divergent as well. So we just showed this is divergent. So it means our original one is divergent as well. So we don't even need to check that other improper integral. I mean, we could for practice, but since that one we checked, the integral from 0 to 5 is divergent, then the other one doesn't stand a chance. The integral from 0 to 7 of 1 over x minus 5 is divergent as well. All right. So these are just kind of other ways we can have improper integrals. And really, they all center around this idea of our function has a discontinuity somewhere in that interval we're trying to integrate across. All right, so that's going to do it for our different cases of improper integrals. Next time what we're going to see is we're going to, well, we're going to look at more improper integrals. We'll get one more in there. And these are, the next ones we're going to look at are a very specific case of, well, we're going to be using it when we talk about series and sequences, which are coming up pretty soon. So the next set of improper integrals that we're going to be looking at, really we want to understand because we're going to be using them quite a bit coming up when we start talking about sequences and series. So we'll see that next time. So have a good rest of your day, and we'll see you tomorrow. Bye-bye.